Hello. So in today's lesson, our learning target is I can identify characteristics of quadratic functions, such as x and y intercepts, the vertex, the maximum and minimum, and the axis of symmetry. So in our last couple lessons, we went over how to solve quadratic equations algebraically. So going forwards, we're going to switch from just looking at quadratic equations to looking at quadratic functions. So a quadratic function is essentially a function that is quadratic. I guess pretty self-explanatory. And in standard form, the equation of a quadratic function will look like f of x is equal to a x squared plus bx plus c. So we're familiar with this standard form from when we were factoring quadratic equations. But now I want to delve a little bit deeper into the graphs and the characteristics of these functions themselves. So same format, we have three constants. We have a, b, and c. We have an x squared term, an x to the first term, and a zeroth order term without an x. And the graph of a quadratic function is called a parabola. So the graph is a parabola. So I'm just going to make a sample graph, a quadratic equation, that could look something like this. So all parabolas are always either going to have this U shape, or they could also have an upside down U shape, and we'll discuss that situation a little bit later in this lesson. But now we want to look at some of the characteristics of the quadratic functions. So in the last couple weeks, we were solving for the zeros or solutions of quadratic equations. So when we go from quadratic equations to quadratic functions, those zeros are the x-intercepts. So these would be the x-intercepts, also known as the zeros of the function. So in order to find the x-intercepts of a function, quadratic function, we'd use the same method that we were using before to find the zeros. So just like how we went over quadratic equations could have 0, 1, or 2 real solutions, it's the same deal with quadratic functions. So we could have a function that I guess just barely touches the x-intercept, so this would have just one x-intercept. Or we could have a function like this, and this is not going to have any x-intercepts. This would have 0 x-intercepts. So, so those are the x-intercepts or zeros of the function. You can find them by an equation finding the x values where y is equal to 0. So we can just do a quick example of finding the x-intercepts. On a graph, you can just look and see, okay, where does my graph cross the x-axis? It's going to be at, say, -3 and +12 in this case. So the x-intercepts would be x equals -3, x is equal to 12. If we're given an equation, say we're given f of x is equal to x squared plus 5x plus 6, we would just set this equal to 0. And now, once we get the equation into this form, hopefully we're in our wheelhouse. This one we can see can be pretty easily solved by factoring, because 3 times 2 is equal to 6, and 3 plus 2 is equal to 5. So we can say this is 0 is equal to x plus 3 times x plus 2, and our x-intercepts will be at x is equal to -3, x equals -2. So those are the x-intercepts of the function. Additionally, all quadratic functions will cross the y-axis at some point. So we have the y-intercept right here. And again, by looking at the graph, you can find the y-intercept by just looking at where it is. So in this case, say this is, say, -8 would be the y-intercept. And then if we have a quadratic function in equation form like this one, we would find the y-intercept by finding the y value where x is equal to 0. So recall that f of x is equal to y, which is equal to x squared plus 5x plus 6. So if we want to find the y-intercept, we would just find f of 0, that'd be equal to 0 squared plus 5 times 0 plus 6, which is just equal to 6. So that would be our y-intercept for this quadratic function. So that covers the y-intercept. So next up, we want to find the vertex. So much like absolute value functions, quadratic functions have a vertex, which is kind of the point at either the bottom or the top of the U. So that's going to be right here. So we can find the vertex on a graph by just looking at the coordinates. So here the vertex will be at, say, 6, -14, for example. Whereas finding the vertex algebraically is a little bit more difficult, and we're actually going to go over that in our next lesson when we go over how to graph quadratic functions. So there's where our vertex is. And then additionally, while we're talking about the vertex, we can also talk about maximum and minimums, because our vertex, I'm going to switch colors, our vertex is also a maximum or minimum value. So you can see in this case, our vertex is our minimum value, because maximum and minimum refers to the y-axis. And here you see our graph goes down, and it reaches its lowest point, or minimum value, at this vertex. And then it starts going up again. So we have a rule here that we're going to come up with. So if a is greater than 0 in our standard form, so say we have like f of x is equal to 2x squared plus 4x minus 15, then our vertex will be a minimum. However, if a is less than 0, so if this coefficient is negative, so I'll just, example, -5x squared minus or plus 3, then we're going to get the upside down U shape, and our vertex is a maximum. And in that case, you see we're following the graph, we're getting higher and higher and higher, and then we reach our peak, the top of the mountain, and then we go down. So this is both our vertex and a maximum. So again, we went over how to find these when it's graphed for us, but in our next lesson, we're going to go over how to find these algebraically when we're given the equation of a function, which is also going to be just a very useful skill for us to have in general for graphing. So now, I guess the last thing I want to go over is the axis of symmetry, which I already have partially mapped out. The axis, so one of the defining characteristics of parabolas is that they're symmetric, meaning that if you draw a line through the middle of the parabola, each side is going to be a mirror image of the other side. So the line of reflection, which I already have partially drawn here, is called the axis of symmetry. So you can see, to find the axis of symmetry of a parabola, you just draw a line right down the middle going through the vertex. And in this case, our axis of symmetry would have the equation x is equal to 6. So we use the x value to define the axis of symmetry. In this case, this would be our axis of symmetry. In this case, this would be our axis of symmetry, and so on in these two cases. So again, the axis of symmetry, it's kind of the line of reflection, and you see that this side of the parabola is symmetric to this side. So the axis of symmetry is actually fairly easy to calculate algebraically too. So we'll go over that right now just really quickly. If we have, say, f of x is equal to 4x squared plus 20x minus 14, the axis of symmetry is defined by the equation x is equal to negative b over 2a. So in this case, b is equal to positive 20, a is equal to 4. So our axis of symmetry is going to be equal to negative 20 divided by 2 times 4. So that's going to be equal to negative 20 over 8. It's equal to negative 10 over 4. Equal to negative 5 halves, or negative 2.5. So that is how you find the axis of symmetry algebraically, just really quickly, and we're going to go over that much more in depth in the next video, which is going to be on using these skills to actually graph quadratic functions that are in standard form. So that's it for today. Stay tuned for the next lesson if you want to learn how to graph quadratic functions yourself.